we have defined the stress vector as limit delta A tending to 0 of the incremental resultant vector divided by the area, small area. Now what do I do is that this just like we resolved the resultant force along the 3 directions n and S1 S2, I will resolve this delta F star incremental force along the 3 directions which you have chosen, okay. That is what we will do now. So resolve into components along our chosen coordinate system n vector S1 S2 vector, okay. Okay. So normal to the plane and then tangential to the plane, okay. So now let us do that, because if you talk about force it has all the information, but what is more useful is if you talk in terms of components, okay. If you keep talking about velocity vector, that is fine, but you always talk in terms of velocity components Vx, Vy, Vz, okay, fine. So what is that I have done? This delta F star has been resolved along the n direction denoted as delta Fn, along S1 delta Fs1, along S2 delta Fs2, divide by area, of course limit delta A tending to 0. So this is a component representation of this equation given in the first bullet, that is in terms of incremental vector itself, but now it is in terms of the component of the, let us say this is the Fn is the normal component of delta F1 represents the incremental normal force, and then this is the incremental tangential force and the incremental tangential force along the respective directions, okay. Okay. Now we will take the limit, we apply the limit for every component, okay. So that is why it has been shown split into components. So we will apply limit for delta Fn by delta A, delta Fs1 by delta A, and similarly the other component as well, okay. Now we will define this incremental normal force divided by area as the area tends to 0 as the normal stress. Why is it normal stress? Because that is acting normal to the plane. So this is definition of stress vector, because we are split into components. This term, that is incremental normal force or the normal component of the resultant force, we want to be very specific, divided by area as the area tends to 0 is denoted as tau nn, which is normal stress. Now similarly the second term, that is the incremental tangential force divided by area, tangential force along S1 direction in the limit of delta tending to 0 gives you the one of the shear stress component. Why is it shear stress? It is acting parallel to the plane or along the plane, okay, tangential to the plane. Similarly along the other direction you have the other component of shear stress. So you have normal stress component tau nn and then 2 shear stress components. As I told you, because it is on the plane you cannot have one, even if you have one you will have to resolve along 2, that is why you have 2 shear stress components tau n S1 and then tau n S2, okay. Now let us understand the meaning of the subscripts. That first subscript represents the direction of the plane, and then the second subscript represents the direction of the component, okay. This has to be kept in mind, this is going to play a major role as we go along. Just to repeat, the first subscript n represents the direction of the plane, second the direction of the component, okay. Now all these whatever you have discussed is shown diagrammatically as a figure in the right hand side. What is shown? The stress vector is shown Tn, and then the normal component, the normal stress is shown, and then the shear stress components tau n S1, tau n S2 are also shown. Normal component is along n and the shear stress components are along S1 and S2. What is that we have done? Earlier we resolved F star, the whole resultant force along n S1 S2. What we have done now is resolved Tn vector along n S1 S2. What is the difference? Resultant is over a area, over a averaged over a area, but now we have resolved what is the stress vector acting on a plane at a particular point, that has been resolved along normal direction and the tangential directions as well. Okay. So, to summarize this slide, we have introduced the normal stress and the shear stress components. Okay. Of course, in terms of terminology we have discussed components of stress vector, the normal to the plane is a normal stress, and tangential to the plane are the shear stresses. So, one component of normal stress, two components of shear stresses. Okay. Now, we said at a point, please imagine this to be somewhere inside the object. At a point we have drawn a plane and identified as n. And you also mentioned that you can same point you can consider several planes of different n vector, and that is what is shown here. Same point, please remember, it's the same point, but the orientation of the plane is can be different, which means that the n vector will also change based on the orientation, the n vector will also change. Now, which becomes little inconvenient for us because our coordinate system is attached to the plane, it is associated with the plane. So, every based on the plane you consider, this will have one n vector s1 vector s2 vector, this will have another set of n s1 s2, similarly this will have n s1 s2, which becomes very inconvenient for us, and that is why what we do, we consider the plane, any plane, but now instead of choosing the coordinate axis associated with the plane, we resolve the stress vector along our usual x y z axis. Is that okay? Why is that? Because the earlier we want, of course obvious, what is that is required for us is the normal stress and the shear stresses, but the way in which resolved is difficult. We will find out that as we go along, but right now instead of resolving the stress vector along n s1 s2, I resolve the stress vector along the our usual Cartesian coordinate systems directions, namely x, y and then z. Okay. I like to mention the books, of course you would have observed the previous figures are all from Raymond Parnas, and then this particular and few other figures are from the book Stress and Strain by W. D. Means. I did mention about this in the introduction, a very good book to understand about stress, split into very small chapters, looks like, in fact looks handy like a story book as well. So, strongly recommended for understanding fundamentally about stress, relatively a difficult concept put nicely, very sequentially, systematically, in terms of slowly building on the concepts in this particular book. Okay. So, coming back, the stress vector has been resolved. Now, what is the nomenclature you will give? Okay. Remember, the stress vector T n was resolved along n s1 s2. So, the notation was that the first subscript represents the direction of the plane, that is not going to change, we are still considering any plane. So, the first index there is no change, the first subscript there is no change. Now, remember the second subscript represented the direction of the component. Now, we are resolving the stress vector along the x y z coordinate, that is why second subscript has been now changed to x y z. So, understand the nomenclature, tau n x means that tau n x, tau n y, tau n z, in all these variables n represents the direction of the normal to the plane, and then the second subscript represents the direction of the component of the stress vector. Okay. Now, the same thing has been shown in two other different ways nicely in this book. Look at this, this first figure shows the component of stress vector along x y z axis, tau n x, tau n y, tau n z. Okay. Of course, the coordinate axis has different orientation, but as usual if you look at in this direction, if you look at this direction, this is our usual x y z coordinate system. Okay. The figure in the middle shows the same information in slightly different way, the way in which you construct the stress vector. Let us say you have tau n x vector is drawn parallel here, and then you have tau n z. Let us say you add this, you will get this vector, and then to that you add tau n y, you will get this stress vector. So, the construction of stress vector is nicely shown, that is why this book is very good in terms of understanding. Once again, example is also shown here. For example, what is shown is we have chosen a value of tau n x equal to 3 kilobar. Of course, all stress units are force per area. So, that is why the unit is kilobar, something like our pressure, okay, kilobar, and then tau n y is just 1 kilobar, okay, and tau n z is 2 kilobar. This 3 kilobar is for representing the scale, okay. So, now once again the same construction is shown here. Let us say you take this 3 kilobar and then this 2 kilobar, you get this vector, to that you add this 1 kilobar and you get this stress vector, okay. So, very good representation of the stress vector resolved. Remember, the plane is still any plane, I repeat this because we will relax that as well as we go along. On any plane, the stress vector acting, remember all these are point values, already we have taken limit. You have a plane, at a point you are resolving the stress vector along x y z axis, and they are called as tau n x, tau n y and tau n z, okay. Okay, now let us proceed. What is that we have done? We have resolved the stress vector in two different ways, okay. That is what this slide is about. Stress vector is same, remember T n is same, the left hand side that is same, the way in which I resolved is only is different. In the first case, we resolved along coordinate axis associated with the plane, we resolved along n, resolved along S1, S2, and hence represented as tau n n, tau n S1, tau n S2, and the unit vectors were n vector, S1 vector, S2 vector. Same stress vector only has now been resolved along our usual x, y, z Cartesian coordinates, and that is why the unit vectors are now I, j and then k, and then now the components become tau n x, tau n y, tau n z. Please note the first subscript is still n, the same plane, only the second subscript has changed because the coordinate directions along which you are resolving is different in both the cases. Stress vector is still same, okay. And of course, the components here are tau n n, tau n S1, tau n S2, and in this case tau n x, tau n y, tau n z, okay. And remember, same stress vector, same plane, same point, everything is same, okay. Now, as I was telling you, we have considered any arbitrary plane at any given by n vector. If you look in terms of hierarchy, first we said any plane, and then we said any coordinate direction, because the coordinate direction associated with the plane, which means any plane, any coordinate directions. That is very generic, very difficult to handle. We want some form of uniformity, some form of generalization, some way of representing in a universal way. That is why we said we will consider any plane, but we will resolve along x, y, z coordinate direction, becomes a little bit simpler to handle. But even this is difficult, because though we are interested in stress acting on any plane, we will make it little more easier to handle. Instead of considering this any plane, I consider the planes which are parallel to our coordinate axis, okay. That is why as shown here, remember all these planes are at the same point, you will understand that as I show further figures. At the same point, when I say plane, you should imagine a very small plane at the same point. Instead of considering plane of a normal n, you are considering our usual planes which are parallel to the coordinate axis. What are the planes? xy plane, yz plane and zx plane, okay. That is what is shown here. What is now shown here? Stress vector not acting on that our plane, n plane, it is stress vectors acting on the we do not call as x, y, y, z, zx plane, we call in terms of the normal. That is why we denote it as stress vector acting on x plane. What is x plane? x plane is one for which x axis is normal. So, in this case it is something like this. Okay. So, T x, T y, T z, of course I will discuss more on this in future slides. As of now we have moved one step, I would say closer to in terms of understanding and easier to represent, that is more important. So, from any plane, any coordinate directions to any plane, but x y z coordinate directions. But now see, look at the organization, becomes more and more organized, now easy to understand. These planes are very well known to us and coordinate axes are also very familiar to us. Of course, finally we will have to go back to this, because our interest is on any plane what is the normal force acting, what is the shear force acting. We will have to come back to that, but now we are breaking down the problem into simpler and simpler conditions. Okay. Okay. Now let us discuss more about this in the next slides. Okay. Now what is shown here, earlier we have in the slide prior to that we have resolved the stress vector on any plane along x axis, y axis, z axis. Okay. Now instead of that any plane I have a well defined plane. As I told you, this is the plane which you call as x plane, or actually the plane is in the plane of y z axis. So you can call either as y z plane, but we have denoted the plane by the normal to the plane. So according to our nomenclature it is x plane, the x axis is normal to this plane, hence it is called x plane. So we will use this nomenclature in further discussion. When I say x plane, usually immediately let us say this is your x axis, you should imagine this axis x plane. The plane to which x axis is normal, that is a big sentence has become x plane. Okay. Now Tn is a stress vector acting on any plane. Now what is the notation? Should be Tx, because our x is the normal and that vector is shown here Tx. Now just like tau n x, tau n y, tau n z were components of Tn, we will introduce tau xx, tau xy, tau xz as the components of stress vector acting on x plane. How do you interpret that? Let us how do you understand that? Let us look at this first representation of stress vector acting on any plane. So this, that is why the first subscript was n, we resolved along coordinate axis associated with the plane. So second subscript is n s1 and then s2, and the coordinate directions were n s1 and s2. Next step, what did we do? We resolved along x y z axis. So unit vectors became I, j, k, and the components still had n. Look at this, the first subscript is still n because it is any plane, but now because we resolved along x y z axis, the second subscript became x y z. Now we have made one more simplification, the plane is not any plane, it is x plane. So I am replacing this n with x, this n with x, this n with x, hence I get tau xs, tau xy and tau xz as the components of the stress vector acting on x plane. Okay. So now tau xx represents the normal stress and tau xy, tau xz represents the shear stress. Okay. On which plane? On the x plane, normal stress acting on the x plane and then the shear stresses acting on the x plane, and that is shown here also nicely here. Look at this, the tau xs is a component, of course you can have any component, it is now along the negative x axis, and you have tau xy here and then tau xz here. Now as we have constructed here, I can construct here also. Let us take these two components, then you will get this vector, okay, and then to that you add this tau xs, this vector, you will get Tx. Okay. So you take these two, you will get this vector, to that you add this vector, you will get Tx vector. So nicely shown the construction. Of course other directions will be much more clearer. So what we have done here is moved from any plane to the x plane and resolve the stress vector acting on the x plane into its components along x y z axis. Okay. Now just quickly we will do for the other coordinate planes as well. Remember, once again I want to repeat, at the same point instead of our general plane we are considering 3 planes which are parallel to our coordinate axis planes. All these planes are at the same point, not at different points. Okay. Now this is the y plane. Of course this picture is much more clearer. What is the y plane? This is y plane because y axis is normal to the plane. Now the stress vector acting on the y plane is Ty. So as we have done earlier, this the components are denoted as tau ix, tau yy, tau yz. Why is that? The first subscript represents the direction of the plane, it is y, second subscript the direction of the component, so x, y, z. So these tau ix, tau yy, tau yz are the components of stress vector acting on a plane whose normal is the y axis. Okay. And once again the construction is shown nicely here. What are the components? Tau ix, once again for example taken a direction against the positive x axis, and then we have tau yy along the y axis, tau yz along the z axis. So you can construct let us say if you take tau yy and tau ix, you will get this vector. To that if you add the component along z axis, then you will get the stress vector which is Ty. Okay. Of course we have seen that they denoted as y plane. Now analogously we can discuss z plane, very clear picture here. Of course this is a z plane because z axis is normal to the plane, and the stress vector acting on this plane is Tz resolved along x axis as tau zx, and then tau zy along y axis, tau zz along z axis, and this stress vector acting on the z plane is represented as tau zx, tau zy, tau zz. Take away from all this is the first index represents the direction of the normal to the plane, the second subscript represents the direction of the component of the stress vector acting on the respective planes. Okay, this summarizes whatever we have discussed. So components of what is shown here, components of stress vectors acting on 3 planes parallel to the 3 coordinate planes. So this is the x plane, the y plane and the z plane, and all the components. So we have totally 9 components now, tau xx, tau xy, tau xz. Similarly here tau yx because y plane, tau yx, yy, yz, and z plane. So we have tau zx, tau zy and tau zz. All these are so represented vectorially, components of stress vector on x plane, and then the components of that stress vector. Stress in this diagram, of course stress vector is not shown, only the components are shown, stress vector on y plane and the components, stress vector on z plane and the components. The same representation, little more colorful, from a recent book. I think I should mention about this book and the website. Please note the website, very look at the title of the book, it says Mechanics of Materials, an integrated learning system. Extremely well presented book, and the website is more of animations are there. The entire subject of mechanics of materials are represented in terms of animations and movies, and very interactive and easy to learn also. So and even look at this picture, the way in which they are represented shows like a 3-dimensional view. You have x axis here, y axis here, z axis here, you have shown some wall like and a floor like surface, becomes very clear. And this also shows very clearly that we are at the same point q, okay, and then now we are considering the body is cut along using a plane which is perpendicular to x axis here, same point, same, that is important, okay, same point, the plane is now perpendicular to the y axis, now the plane is perpendicular to the z axis, and of course the components are shown here, tau xx, tau xy, tau xz. Similarly tau yx, yy, yz, and then zx, zy, z, little more colorful representation of what we have been discussing so far. That is from Raymond Partners, and this is from this book by Philpott. Okay, to summarize whatever we have discussed so far, just putting in sentences, just 3 bullets. The internal forces on a plane of finite area is represented by a resultant vector f star. Okay, f star was over a finite area. The ratio of resultant force per area as the area becomes very small, tends to a point, is defined as a stress vector, also called as traction vector. Okay. That is why it is called Tn. Okay. And objective is to calculate the stress vector. That is our objective. Remember, always only to simplify things we have moved to from any plane to any plane xyz coordinate axis, and then to 3 well defined planes. Objective is to calculate the stress vector, that is the components of stress vector tau nn, tau ns1, tau ns2. Okay, that is objective.